Hi there, welcome to your lesson on modeling using sine and cosine. Let's begin with the sine curve. As a reminder, the sine curve is a wave. It flows like this. And the cosine curve is a similar wave, just translated horizontally. So the cosine curve looks like that as well. However, it begins at 1. Alright, so we have these two waves. These waves can be used to represent many things in the real world. Therefore, they're a very important family of functions to know and understand. So periodic occurrences, these curves, first of all, are called periodic curves because they have a repeating pattern. So for example, here we have a wave, and that wave repeats to infinity. This is called periodic behavior. So periodic occurrences happen in repeated and predictable cycles, such as lunar orbits and high tides. However, many real-life situations are more complicated than the simple rotation about a unit circle. We often need to transform the sine and cosine curves so we can use these functions to model an event. What that means is we know the sine and cosine curve have a high point of 1, a low point of -1. They have a period of 2 pi. So that's your basic function. But obviously, not everything we want to represent in the real world like this has a height of 1 or -1 and has a period of 2 pi. So we're going to have to transform our functions to make them proper models for things in the real world. So here's an example of tides, and we can see during the day the tides go up and down, up and down. That's definitely periodic. We can use a sine or cosine function to model that. And notice again, yeah, one period, so from bottom of the wave to bottom of the wave, it's 12 hours here, it's half a day, and that's not 2 pi. So we're going to have to transform a function to model that. Okay, here's an example of some lunar orbit inclination. So as the moon goes around its orbit around the Earth, we can measure its positions in the sky, and it follows a periodic pattern as well. Okay, a problem we looked at last time is, though, kind of a nice starter problem for this. Okay, so a common starting place for modeling with sine curves and cosine curves is often this Ferrous wheel problem, and we talked about this one with the London Eye, a very famous Ferrous wheel. So let's take a look. Here's a little information about it. It was opened in the year 2000. It has 32 capsules that people go into. Each one can carry 25 people, so they're quite large. It's a very big tourist attraction with about 3.5 million visitors each year. The London Eye takes approximately 30 minutes to complete one revolution. So if you sat in there, you would get a 30-minute trip. It is about 135 meters tall at the highest point, and a passenger in one of the capsules travels in a circle to complete the revolution. We'll see what the function looks like, but basically here is the function representing the height of the person based on time. So again, during their whole 30-minute trip, this function will produce all the different heights they reach as they go around this circular Ferris wheel. Let's take a look at dissecting this and looking at transformations, because that's what will help us jump into our lesson today when we model using these functions. So hidden amongst all these numbers, we do see a cosine function. So we know there's going to be a wave here. Let's break it down a little bit. The number in front is the amplitude. So the amplitude is 67.5. So that means the wave, which used to have a height of 1 for the normal cosine curve, now has a height of 67.5. So that's our amplitude. The period is how long it takes to do one full cycle of the wave. A normal cosine graph has a period of 2 pi. The way we can figure out the period is looking at this number here, which is inside here in front of that. So this here, when you get the period, so the period is calculated this way. We take 2 pi, which is a normal length of a period, and we divide by b, which is this value here. So if you take 2 pi and divide by this, it's like saying 2 pi divided by this fraction, which means we can multiply by the reciprocal of this fraction. So 2 pi times 30 over 2 pi. The 2 pi's cancel, and we get a period of 30. Now this should start making sense, because we just said that the Ferris wheel takes 30 minutes to complete one trip around the wheel. So there's our period of 30 minutes. All right, phase shift. Phase shift is the left to right movement of the wave, and that can be determined by a horizontal translation. And as you may remember, horizontal translations are here with the x value, or the independent variable, so in this case t. So this tells us that the graph has moved over 15 units to the right. So our phase shift is 15. And vertical shift, the up and down shift, is the one when we translate the entire function up or down. And that can be found by the number that we add or subtract from the entire function. So it's this number here. So our vertical shift is 67.5. Notice it's the same as the amplitude, and we'll see why in just a second when we look at the graph on Desmos. So let's go to Desmos and check it out now. So here is a basic sine graph. You can barely see it there, but you can see the wave. And the reason it's so small is because soon our wave is going to get very big because of the transformations we've done. So I've started with a window ready for the big ones. But the little one there, that wave has an amplitude of 1, so it goes up to +1, down to -1, up to +1, down to -1. It has a period of 2 pi, so that means a full wave takes place in 2 pi, which would be about 6.28. And we can see a full wave just barely there, 6.28 length. All right, but we're doing some changes. So the first change is we did an amplitude of 67.5. So watch what happens. Well, there we have it. All right, so we still have the same width of the wave. Notice here in red, the wave goes up and down, right? And here it also goes up and down, but now it has a height of 67.5 instead of 1. So there's our amplitude. The next change we applied was this. And if you remember that number there, the b value inside there, it represents the change in period. And when we calculate the period, we found out it's 30, right? So watch what happens to the wave now when I click this and this transformation is applied. We see now the green one and the period. So I'm going to erase this one so it's not there. We see now the period is 30. You can see that, for example, from, let's say from here to the next peak, right here, and it's 30. So now it takes, to do one full wave, it takes 30 instead of 2 pi. Before it did in 2 pi, which is 6.28. So now it's stretched out. It takes 30 units to get one wave done. Great. Next transformation, what do we see? Oh, we see this translation here, and this is a horizontal translation, 15 units to the right. So that means this entire curve will shift 15 units to the right. So why would we be doing that? Let's take a look at what happens. Okay, so it moved 15 units to the right. Okay, we'll see why we did that in just a second when we do the other translation. Okay, so far it moved, so I'm going to get rid of the green one, and now we see it shifted 15 units to the right. The shape is still the same. Now the final change we did is this 67.5 at the end, and that is our vertical translation. So the whole curve will move up 67.5. So why? Remember the amplitude right here is 67.5. That means the height of the wave from here to here is 67.5. And when you're sitting in a Ferris wheel, you never go underground. You don't go a negative distance, right? This wave is supposed to represent your height when you're sitting in the Ferris wheel. So you should never have this negative bit. So if the amplitude here was 67.5, then this part here will also be 67.5. So now if we want to shift the whole thing up so that it has no negative portion, we move it up by 67.5. So let's check it out. And there it is. See, the whole wave moved up 67.5. Now get rid of the purple one, and there's our final result. So the original cosine graph in red, and now this one here, you can see it in black. And you can see now, so as time begins, you're at your low point, and then you're going around the Ferris wheel, your height is going up. You reach your maximum height of 135, because we know that's the height of the Ferris wheel. And then that's the high point, and that's halfway through your journey, 15 minutes. And then you're coming down, down, down until you get to the end again. You're done your journey. 30 minutes have passed. Your height is now 0 again. So here's one full wave and one full part of your journey. Great. That's how we can take a basic cosine curve or wave and turn it into something that models something in real life, where all the numbers have meaning in the real life context. Let's go back to our presentation and move forward with that. So welcome to Real Harbour, UK. We're staying in the UK. This is a famous harbour in the UK that's known for how much the tides go up and down. So check this out. Here's one photo, and here's another photo. Look at that. The water level dropped dramatically. And that happens in lots of harbours, but this one's very well known for it. So tidal behavior can also be periodic, which we can model using sine or cosine. So here is a situation. Ben is a fisherman with a boat at Real Harbour. This is part of the graph showing the depth of water at the mouth of the harbor. So you can see here at time, this is hours after midnight. So 0 hours after midnight means at midnight, the water depth was what looks like 3 meters. And then 4 hours after midnight, so 4 in the morning, the water depth is 8 meters. And then after that, it goes down again. And 10 o'clock the next morning, the water level's down to 2, and so on and so on. The tides are coming in and out. So find the amplitude of the function. What do you think? And here's how we do it. We find amplitude by finding the difference between the max and the min points. So we know the max is 8 here and the minimum is 2. Okay, so we do max minus min, 8 minus 2, and we divide that by 2. That will give us our amplitude. Why are we dividing by 2? Because the amplitude is only the height of the half of the wave, right? So if we found out the amplitude is 3 by that, we know we have this center line here going through the graph, right? If we found out the amplitude is 3, then means the center line of the graph must be 3 away from the max point, so 3 down, down to 5, or 3 up from the min point, from 2 to 5. So 5 is our midline, and then we can see our amplitude clearly here, 3 and 3. So that's our amplitude. Now, find the period. Okay, so what's the period? Remember, period is the time it takes to finish one wave. One thing I would recommend when you have a wave that's been moved around is just go from top point to top point, or bottom point to bottom point. That will help you get the period. So what is it? What's the period for this one? Okay, let's check. I can begin here and go to here, and from there to there, the distance is 16 minus 4, that means 12 units to get across. Okay, so our period is 12. Now next, find the horizontal shift. So how much did this graph move horizontally? It means left to right. That's also known as the phase shift. And think about where the normal cosine graph begins. That should help you answer this. Okay, the horizontal shift is plus 4 units. Okay, horizontal shift plus 4 units. Why? Because a cosine graph always begins at its highest point on the y-axis. And this one we can see the highest point is here. So we can say the whole graph moves over 4 units like that. Okay, next, what's the vertical shift? And now think about, where does the cosine curve normally sit when you're thinking about it horizontally? Because obviously this one has moved from its normal position of the basic cosine graph. Okay, how much has it moved? It's shifted up 5 units. Why? Because normally the midline is on the x-axis, right? And then the curve goes above and below, above and below. So it moved up 5 units to get to here. Okay, now that we have all those pieces, we can make an equation. So let's make the equation in pieces. First of all, here's a basic cosine graph. And now think about the changes we've done one by one. So first, let's apply the amplitude. What should the new function be? Well, it should be 3 cos theta. The amplitude always goes in front. That tells us the waves are now, instead of having a height of 1, the waves now have a height of 3. Great, we've taken care of that. Next step, let's take care of the shifts. That means the horizontal and the vertical. Put those both into the equation. What do you get? Well, here's our 2 shifts represented there. Here's our vertical shift, up 5 units, and here's our horizontal shift, right 4 units. Okay, next, let's take care of the period. And this is always the one that's trickiest. But remember, period equals 2 pi over b. Okay, so in this case, we know the period is 12. We figured that out. So period equals 2 pi over b. Now solve this for b. So I'm going to move the b here and move the 12 under there. So I end up with b equals 2 pi over 12, which reduces to pi over 6. So that is where our period, that's where our b value goes, which helps us determine the period. Great, let's move on. Let's apply this to some problems here. Now that we have a function, so there's the function we came up with, and now it says rewrite the function in terms of m and h, being the 2 variables here. So here it is, rewritten like that. We have m, the dependent variable, the depth of water in meters, and h, the input, the hours after midnight. So I've just rewritten the function using m and h. Okay, now calculate the depth of water at 9:30. So our input is 9:30. What would that be? Well, our input would be 9.5. Put that into the function, calculate it, what do you get? Okay, we get 2.1, and that we can confirm that on the graph. 9.5 would be about here, 2.1 meters of depth, makes sense. All right, last question. Ben's boat can only get in and out of the harbor when there is at least 4 meters of water in the harbor. Ben sleeps until 10, so he sleeps until 10, that's where he wakes up. Here's a line representing 4 meters depth of water. So find the next time he can go fishing. So if he woke up here, when's the next time he can go fishing? He can only go fishing when the water is level above 4, right? So you're looking for this point. So graph it. Use your graphing calculator. Graph this function. And using y2, graph the line y equals 4. Graph them together and find this point of intersection. That point is that value there.